Hi everyone, thank you for joining us today, and we're super excited for the TensorFlow Everywhere event, and we hope you are having a great Thursday evening. I'm Jiaxing from the Google Developers Relations team, and this is Sam and Martin from TensorFlow and Deep Learning Singapore. Yeah. Before we begin today's session, let me briefly introduce who we are and what we do. Google Developer Space is a platform for developers and startups from around the region to learn and connect with one another. And as part of the developer relations team, we aim to empower and connect the community to our people, programs, network, and technologies. We are really excited for the awesome speakers and sessions we have lined up for you today. And without further ado, I'll hand the stage over to Sam and Martin to share more.
Okay, thank you, everyone. It's been a long time, right? We haven't done an event for quite a while. This is the first event we're doing with StreamYard, so we're just sort of learning the ropes of this. But Martin, you want to say anything before we get started?
Well, it's been just over a year since our last Everest meetup, and our last after party in McDonald's. I mean, what a time that was. Right?
Yeah, unfortunately tonight the after parties are going to be limited to 8.
Okay, take it away.
All right, let's get started. So, all right. So tonight I'm going to be talking about TensorFlow Keras pre-processing layers. So what we're going to talk about, just to sort of give you a preview of the evening tonight, is I'm going to do a session on the pre-processing layers. Martin's going to talk a little bit about TF NumPy, some of the new things there, also the new additions to TF Profiler and some of the research stuff. And then we've got a Google developer advocate, Robert, who was here in Singapore it was June or July 2019. And he's recorded a talk. Unfortunately, I think it's quite early in the morning in San Francisco at the moment, but he has recorded a talk for us, and we're going to play that. And we can also, take questions and stuff at the end of this. So let's get started. All right. So a little bit about myself. I'm a Google developer expert for machine learning and deep learning. I generally work with deep learning related to sort of language, dialogue. Lately, a lot of things to do with multilingual sort of stuff. Also very interested in generative models and that kind of stuff. My background is in startups. So I've built two B2C startups with more than 1 million users. I'm also a mentor for the Google Startups Accelerator for both the Southeast Asia and for the United States one. And the startup that I'm working on, obviously, hopefully you can see from this, is Red Dragon AI, which Martin and I are doing a lot of work on. So just a little bit about Red Dragon. We do deep learning consulting, prototyping, research. We've had papers at a number of conferences and workshops and stuff like that. We're also a Google partner. We're very interested in sort of the conversational computing space and sort of digital human space. We'll maybe talk about that more in the future. All right, so let's get started with the sort of Keras pre-processing layers. So what I'm going to be talking about tonight is one of the sort of new additions that has come in the past, probably since about 2.2. Some of the layers have been added in 2.3. There's even a couple of these layers that are going to be added, I think, in a future version of TensorFlow, and they're in the nightly builds. But most of the ones I'm going to show you tonight are already in TensorFlow 2.4. You can go and use them, and all the code that I'm going to be showing you today is, I'm going to be running in 2.4. So a little bit of background. Obviously, for deep learning models, we have to write a lot of sort of pre-processing logic, and this can be really time-consuming. It can be a real pain to sort of write it, and then one of the really sort of draining factors is that not only do we have to write it for when we're training, we then need to think about how to do this for when we're actually serving and when we're doing inference and stuff like that. So when we deploy a model, often you'll need to sort of ensure that that text or something like that is being processed exactly the same as it was in the training example. And really, this can end up being a lot of work. So what these new layers sort of do is allow us to basically take some of this pre-processing and actually embed it in the model itself. So one of the biggest factors, for this is that it allows you to sort of save a lot of time and money as well. So if you look at this diagram, this is sort of just a very simple diagram of showing you how you might put something into production, where you would run something through on Cloud Run or something like that. Maybe you're storing some images, maybe you're storing some text to a database, something like that. And then you need to go through some pre-processing layers. And if you're lucky, you'll be able to do those pre-processing layers with something like Cloud Functions, so that it would be serverless. But for a lot of things, you're probably not going to be able to do that. You're going to need to spin up a compute engine instance kind of thing. And then finally, you're going to go to your TensorFlow model. And you're going to find that this ends up being quite expensive because you've got multiple microservices going on here. You've got both sort of, something that's having to pre-process data when you're doing inference, and then you've got the actual TensorFlow serving model, and that might be on TensorFlow serving, it might be on, Cloud ML Engine, something like that. But you end up having these two different, machines, and you're paying for sort of two different machines. With the pre-processing layers, it allows you to get rid of all of that and bake that pre-processing into the model. So then suddenly now you only need one, microservice, which is actually serving the model. And it can do the pre-processing in it as it goes along. So, I'm going to sort of talk about, a bunch of things in regards to this. Whoa, that's not the one I want. Okay. All right, so let's look at some of these pre-processing layers. So what are they? They're basically, a user-friendly way to include pre-processing logic as layers inside your actual model. All right. When you save your models, this sort of pre-processing layer will be saved as well. And then it allows you to deploy the models without needing to re-implement, pre-processing on a separate microservice, or running through some other sort of code to sort of do that. Also allows you to run some of the your data augmentation on the GPU directly, so it can speed up a lot of things like that. Okay, there's a whole bunch of these different pre-processing layers. We've got support for things like text, images, structured data or tabular data, and they do a variety of different tasks. So I'm going to go through sort of some use case examples, and I'm going to walk through some code and show you as we go along. So there are a lot of these layers. I'm not going to cover all of them tonight. I'm just going to cover some of the main ones, but there are a whole bunch of them. And you'll notice that a lot of these layers are actually in this, layers.experimental pre-processing. So eventually, these will go from being experimental into just this, standard, just into standard layers. But for the time being, there are some things that, that they're still experimental. That said, they're very stable. We're not talking about, something that's, probably not going to work, though they may probably have some features added to them as they go along. And certainly there are new layers that as people realize, oh, we really need a layer that does X or Y or something like that, people are adding that. So let's look at, a standard thing that you probably want to do. One of the most common things that you will want to do with a deep learning for pre-processing is run some sort of normalization. So this is where you want to do some sort of feature-wise normalization of your input features. We want to basically get this, especially if we've got features, say tabular features that are different ranges. Maybe one is sort of money, one is square feet, one is number of people, something like that. They're going to be very different amounts. So we want to think about normalizing that sort of thing. The other thing too is that often with deep learning networks, we find that the smaller we can keep these weights and biases, the more stable they are, and often the better they do. So, what we want to do is often use this normalization to do something where we're creating a distribution centered around 0 with a standard deviation of 1. It's a very common sort of thing to think about this. So the challenge with this is like, how do we compute this from sort of like our data set to use in the model, or how do we compute this from a sample, a certain size or something like that? In the past, we would have used NumPy to do this. And you probably would have gone through and done a bunch of things like this with NumPy. Now we can use these pre-processing layers, and they will do it for us, and then they will store certain things for them. So this is one of the key things to understand with this, is that these layers often have what's called an adapt method. So the adapt method is, for the pre-processing layers that have an internal state. And it's not a learnt internal state as in like weights of a network. It's a state that is basically, they're not trainable weights, but there's something that you would probably either compute the first time you're starting to do a training, or you can also load them in. So you'll see for things like string lookup, text vectorization, if we've got a vocabulary already, we can load that into these and use that. And then that gets stored in the actual model when we save the model itself. So this adapt method is sort of key, right, as we go along. And I'm going to show you a few different examples of it. Like I mentioned before, one of the other things that you can do is that you can actually sort of preload things. So you will, most of the time, if you're doing something like normalization, you would compute this. But if you were doing some sort of categorical lookup or something like that with strings, you will then often maybe decide to just load that in. So let's sort of look at a few of these. If we were looking at something where we're just doing a plain normalization, let me just go make the code bigger. If we're looking at something where we're doing a plain normalization, we would, basically have some data here. I set up my normalization layer, which is going to be preprocessing.normalization, and then I will just run that. So that layer, has a function called adapt, and I will run the data through that. And then I've got my normalized data, which is going to go into the model. And I'll show you an example in a notebook in a second of doing this. The second way we could do this is with something like a text vectorization layer. So we could then do the same sort of thing. We're just passing in some text into this. This is going to do the text vectorization for us. We then go through the adapt, and then we've basically got our vectorized text, which would go into our model. If we wanted to do it with loading up something already, we've got a vocab, say, for a string lookup already. What we can do is just go into the preprocessing string lookup and just pass that vocabulary in. And in this case, it won't compute it. If we didn't pass anything in, it would look at the data and it would work out what they are. But if we pass something in, it won't do any computation. It will just do it itself. So these pre-processing layers are really key for doing this kind of thing. Now, there are two ways that we can use them. One way is to make them part of the model, which is kind of what I've been focused on. Another way is we can actually put them into our TF data set. And this is more sort of traditional way of doing this. So the model way means that it's going to be really good for inference. The TF data way is perhaps if we want to, if we want all the benefits of TF data, where this is going to be asynchronous, it's going to be buffered before it goes into the model, etc., we can do it that way. So let's look at those in code. In here, you've basically got the first example as where you would use it in an actual model. So I've got my inputs going in, and in this case, this could be raw strings, for example, things that we don't normally put straight into a deep learning network. And then once we run it through the pre-processing, then we can run it through the next part of the model, or the rest of the model. As part of TF data, we can just do a data set and then map to a function. And that could be done, there are lots of examples of mapping, to functions when you're loading data sets and stuff like that. So let's look at, let's jump in and look at some code. So if we come in here and we set this up and we actually look at some models, some actual live code. Hopefully this can be seen. Good. Yep. Okay, so you can see that I'm basically importing the pre-processing layer from TensorFlow.Keras.layers. I'm using the latest version of TensorFlow 2.4.1. And you can see here I've basically got my normalized data. And if I did just with NumPy, if I took the mean and the standard deviation of that, you can see I'm going to get something like this. Whereas if I take the data from the normalized data and I look at those things, I'm going to get, a mean of 0 and a standard deviation of 1. So this has done the normalization of all of this for us. And we can look and see that, like, okay, so what's going into our model is going to be this normalized data set. Now we can specify the axis. I'm not going to go too deep with this, but you can specify what axis you want to do your normalization on and computation on, etc. We can also do this. So we could do this like with NumPy and pass NumPy in. We can also take a full, TF data set. I'm just going to reshape it just to make it nice and simple, and I can pass that through as well. And so here I've basically got my, I've set up, my layer, pre-processing normalization layer. I'm then got some, data. This is what was originally going in. You can see this is what is coming out from the normalizer. And then now I'm going to put that into a model. So in a model, I basically just do it with my inputs, the normalization, and then I just have whatever else I want to have in the model. And I would set up everything like normal, and you'll see that it just trains like normal. If I want to look at that, I can then sort of go in and look at that as well. So I can see what's going on in there. I can also then save that, and I can actually then load that up, and I can see that in that basic, normalization, I can see that this normalization layer has got all these variables in it, but these are non-trainable parameters, right? They're matching what is here. So that's something that you can do. I'll come back and look at the sort of text example in a second. A categorical example would be where we're basically using something like, if I'm going to have some sort of string lookup for categories. So here I've basically got horse, dog, cat, bee, bird, ant. I then set up a pre-processing layer that is going to be a string lookup. I then can basically go through and encode that, and you'll find that that's going to one hot encode each one of these things. So now if this is, if this was sort of setting it up, and then later on I come through and I pass in some features that maybe weren't in my training data, how does it handle those? So we can see that ant was in my training data, so it knows where to do a one hot encoding for that. But things like elephant, if we look back up here, elephant wasn't there, whale wasn't there, and also empty wasn't there. So empty, it always basically sets as the first, the first digit. And then anything like elephant and whale, where it's unknown, it basically sets that as the second digit. So you can see there we've got, basically this one's representing elephant, this one's representing whale. They weren't in the training data. So it allows it, even when the model is going to be training, we are able to sort of go in and use things that, that actually weren't in our, training data. That's fine. Let's look at some things leading into sort of text. So some other nice pre-processing loaders, which I think a lot of people don't know about, are things like, pre-processing where you're basically making a data set from a directory. So you can see here I'm making a text data set from a directory. I could do it with images. I can do it with time series also. And this just basically eliminates the need for pandas and things like that we often use. So with text processing, if you think about basic text processing, what do we normally do? We basically want to do some sort of tokenization. We want to get it into sequences. We want to pad those sequences. Maybe you want to standardize the text where we're going to, set it to lowercase or take out punctuation, etc. These are common tasks for doing it. And this is like the kind of stock standard pipeline that you would use. Maybe where you standardize things to make it lowercase. You're going to split it up into substrings, often going to be splitting on white space for something like that. And then you're going to recombine, these substrings into tokens if you want to do something like n-grams. And finally, you're going to sort of then use that as, get these into integers. So each token is going to be associated to an integer. And then you would pass that into a, embedding or something like that. So one of the new layers that's really good is this layer called text vectorization for pre-processing. And what this will do is it will tokenize the text for us. It will truncate and pad the text automatically, and it will standardize the text based on what we pass into it. So let's sort of have a look at some code for this. And so just to show you very quickly, this is an example of a notebook of doing it the old way. So this is from one of our old notebook from one of our NLP courses. So this is doing sentiment analysis. It loads up a whole bunch of different text files. We then, have to have all this code to basically load them in, to do, removing stuff, to sort of standardize them and stuff like that. We've then got to get some code to split it up. We've got to set up a vocabulary. Eventually, we start to come down to something where we're going to process it, and we're going to use a tokenizer. We're going to use padded, text to sequences. We're going to pad it. This is very standard stuff if you've used TensorFlow, especially over the past few years. You'll notice that's a lot of code, right, that I'm sort of writing there. Let me show you like the new version of that with doing, exactly this using the pre-processing layers. So I come up to the top here. So first off, I've got my data set. That hasn't changed at all. I'm not going to be using the tokenizer. I'm not going to be using pad sequences. I'm going to basically, first off, just get all those text files with just one command. So this tf.keras pre-processing text data set from directory. And I'm basically inferring what the classes are going to be, because if we look back up here, we can see that there's a folder with the negative text. There's a folder with the positive text. So I can infer that. I can, basically export labels with it, integers, also get the class names, set up a batch size, etc. You can see very quickly it's found 2,000 files belonging to 2 classes. I can print that out. I've got 63 batches in here. This is quite simple to do. Here's some examples of the actual text. And then I come to the actual vectorizing the text. So you see already, I've got a lot less code for getting my data in. And then for cleaning the text and vectorizing it, I've got a really tiny amount of code. I've just got this vectorized layer, which is basically going to lower, the sort of standardizing that I'm going to do is just lowercase, strip out punctuation. I could make a custom function and pass that in there. I'm going to have 20,000 maximum features. So in this case, 20,000 words. I'm going to output integers, and the sequence length I'm going to go for is 500 here. So that layer does all of that work for me. Now, one of the things I need to do is, because it's a TF data layer, I've actually got 2 slices in there. I've got the X and the Y. So I've got the actual data, and then I've got the labels for it. So I need to strip that out to get no labels, so that I can then pass this text, pass the data set that we had through this. And that's what it's basically done. Now, I've just looked at the config here just to show you that what it set everything up to be. This is, we don't need to do this, but you can see what's actually going on there. I then basically say, right, I've got my big data set. I'm just going to keep the first 50 batches for training, the rest for validation. I now need a model. So now I'm going to basically run this through. I've got my vectorization layer. If I want to do this, it's going to go into the embeddings here. I've then got my Conv1D. I've got some pooling, very stock standard model, and you can see that very quickly this will train, and it actually does quite nicely, even perhaps better than some of that custom code that was going on before. So this notebook is probably about at least 50% smaller than what it was before from that. So this is where the text vectorization layer is really useful for this kind of thing. There are some times that you probably don't want to use this. So if you're dealing with a continuous language, i.e. languages with no spaces, unfortunately at the moment, the text vectorization really just splits on white space. Hopefully in the future, we may get something like, splitting with more advanced sort of things. For example, like BERT, if you wanted to do some sort of BERT tokenizer, I suspect that may come eventually. The other thing too is that if you want fine control over your padding or truncation, you probably want to use the old way for doing it. So for example, if you want pre-padding where the zeros are at the start and you've got your signal at the end for maybe for an LSTM or something, at the moment it's not doing that. So there are times that you won't want to use it, but for majority of times it's going to be really useful. All right, so the last one I'm going to sort of look at or focus on is image augmentation. So previously in TensorFlow, we've had image ops, and it took a while for these to come. When we sort of asked the TF data team about this, it became pretty obvious that inside Google itself, they have so much data that they don't give a lot of thought to augmentation. But they did eventually add in, a bunch of TF image operations. And these were things like central crop, adjust contrast, adjust brightness, adjust gamma, and stuff like that. And they could do some things like, rotation, flip left, right. But for example, flip left, right. But for rotation, they only went like 90 degrees, which was kind of a pain because really you want to often just angle it a little bit here or there. I just realized here. 1 second. You often want to just angle it a little bit sort of here or there for these things. So where you just want to turn it a little bit to the left, a little bit to the right. And the challenge is all of these are used in data loading. They can't be saved with the model. All right. So with the pre-processing layers, though, now you've got a whole bunch of these augmentation pre-processing layers. And you've got things that, and these act kind of like dropout, where they're active during training, but they're not active during inference. So it makes it really nice that you can suddenly now have a random crop, a random flip, a rotation where you can set, the actual amount of rotation that you want, a whole bunch of these, different things. You also have the actual image pre-processing layers. So if we wanted to do resizing of an image, if we want to rescale it, so rather than 0 to 255, we've just got everything in a 0 to 1 range, we can do that. We can do center cropping, all those sort of stock standard pre-processing stuff as well. And these ones, obviously, we could use them in a model where we're sending raw images to the model for inference, and it will basically just get the pre-processing to the right size for our model, etc. Let's look at an example of this. Let me just go through this. I'm conscious of I don't have too much time left, but okay. So an example of this would be so I'm bringing in the TensorFlow data sets. I'm going to bring in this data set, Stanford dogs data set. You can see that actually I'm going to use an efficient net model. So that works at 224 for the image size. I basically just do stock standard stuff for bringing this in so that I've now got, a nice data set to do this, a TF data set. I can then go through and print out some of the images, and you can see, sure enough, we're getting, these images. We've resized them to the right size for the model. But now let's say we wanted to make like a little mini data augmentation network or image augmentation network here. What we can do is actually make a separate little sequential network. So you can see that I'm making a network here that I'm calling this image augmentation, and it's just a sequential network. I could do it as a functional API if I wanted to, but I've just done it with the sequential API. I've got some random rotation, I've got some translation, I've got some contrast, some flip horizontal, and I've got some random zoom for going into this. And you can see now, if I run that, because this is going to act basically just as like a layer, the whole thing is going to act as a layer. I can now basically run an image through that, all right? And so here I'm just basically taking, these images and sending them through as a batch. And I can then basically play with this, and you can see that sure enough, I'm getting image augmentation. Now, I've kept it reasonably simple. I haven't changed the rotation too much. I've done, left, right flipping, but not, I've done horizontal flipping, but not vertical flipping. The cool thing with this, and you'll see this in maybe this one down the bottom here, is that this is actually automatically doing things like reflection padding. So if you know what reflection padding is, it's basically where if I'm turning the image to a point where where there would have been white space or something like that, it will actually fill it in with reflection padding there. So this allows us then to put this into a model. So this was just sort of printing out some images. If I want to run and train that as a model, I basically just start off with my inputs. I then basically run it through that augmentation. I can then rescale these, after that to be between 0 to 1. And then I can run it into an efficient net model and run that through just like I would. And you'll see that as I, I'm not actually going to do any training, but just to show you this, here what's going on is that it treats this, this is just like a layer now. Because we're using a sequential model in there, that's in sort of the way Keras looks at it and the way TensorFlow looks at it, is that now is just one layer, and that's our image augmentation layer. So you can actually just sort of set something up like this and just use it on every project that you've got, and maybe just fine tune different parts of it, for this. And like I said, when you are doing inference, this will actually be dropped out. So you don't need to worry about that. Okay, on inference, it's going to, do stuff. Now, if you wanted to do something like test time augmentation and stuff like that, you may find that's going to be a little bit harder because it knows on inference not to do that. But anyway, you can sort of see here, these obviously have some, parameters that are going to be, in this case, actually, I don't think it's going to have that many parameters that it's actually storing in there, because these are basically just computational things that are going through. My guess is that the non-trainable parameters in here, part of that is going to be from the efficient net model. But this gives you an idea sort of like of how you could use these pre-processing stuff for image augmentation, as well as, just the sort of standard pre-processing stuff. All right, structured data. You can also use these for things like category, in encoding. If you wanted to do the hashing trick, you've got a hashing layer. In the TF Nightlies now, you've got a couple of different discretization layers, which you can think of as just kind of like bucketing, choosing buckets. So, for example, if we're dealing with age and income, we know that sort of 0 to 18 is almost going to be, zero income sort of thing. So we might set that as buckets and then have the ages going up in buckets of 5 years. We could do that with discretization. You can do categorical lookup sort of stuff. You can do integer lookup stuff. You can also do category crossing, which is basically where we would want to cross features. So for example, let's say we had the feature of longitude and latitude. We'd probably cross those features to get a specific point in that way. Anyway, to sort of wrap up with these, if you want to learn some more about this, I'm going to upload the slides, later on. And there are a number of sort of tutorials that you could go through to sort of learn some of this stuff. Key takeaways, I would say, is, we now have a real simple, easy way for doing pre-processing. It really can save you a lot of money and a lot of hassle to bake these pre-processing stuff into your model, rather than actually, having one microservice that does your pre-proc and one, something like TensorFlow serving, which actually does the model. Image augmentation now has a lot more available than it used to, and I suspect we're going to see that over time these things are going to, are certainly going to evolve. So if you want to get the notebooks that I've gone through, this is the bit.ly link for it, and here's some other ones. Let me just look at some. Okay, so we've got some questions. Let me just bring this in and just take one or two questions quickly. Okay, so hopefully people can see this. Would the preprocessing layers be compatible with TF-Lite quantization and inference on mobile? Okay, so I'm not sure about the quantization part. In theory, these pre-processing layers, once they're baked into your model, they should then become part of the model on TensorFlow JS, on TensorFlow Lite, etc. And that's one of the sort of killer features I really didn't talk about in the talk tonight, is that if you think about it, often doing pre-processing on a phone or pre-processing in the browser of your data can be quite painful, because you're having to rewrite functions that are stock standard in NumPy, or those sorts of things that just don't exist in maybe the Android API, that kind of thing. So this is a way for getting around. I'm not sure about the quantization bit, though. That you definitely need to go through and check out. Another question from Eshra. Actually, if people would shout out, where are you? Are you all from Singapore? So it'd be great to know, for example, how many of you are from Singapore? How many of you from other places? Please, write that in. Anyway, is the pre-processing layers for image augmentation by default only applied to training data and not validation data? Yes, I'm pretty sure it is. Right? When the model goes into validation data, it's actually going into inference mode. So in that case, you're not actually training anything. You are in inference mode, so the pre-processing, the image augmentation shouldn't have any effect on it. It should be just the same as if you're doing predictions or that kind of thing. So anyway, have a play with these. Like I said, I've put up a couple of notebooks for you to sort of try these out. Martin's about to start. Just quickly, we're definitely now much more committed to getting back into doing these events, on a more regular basis. I think we would say. Like I said, we're sort of learning to do it with StreamYard tonight, so we're aiming for sort of March 16th for the next event, which will probably not be TensorFlow related, more sort of deep learning related, more research papers related. There's a bunch of research papers that we want to talk about. This is something that we really are looking forward to getting into. Again, is basically doing more meetups where we talk about this. We're also thinking of doing we've noticed that a lot of people, there are new beginners, and we realize that probably most of the things that we cover nowadays are not from sort of the beginner area. So we might do 1 or 2 events where we just, maybe quite short events, 45 minutes an hour, where we do some beginners stuff and go through that if people are interested. So if you want to, please shout out in the comments what you're sort of interested for doing stuff. For those of you who are in Singapore, I just realized, how do I turn off the for those of you who are in Singapore, we've got some courses coming up with SG Innovate. We've talked about these in the past before. If you are Singaporean or PR, you can claim up to 100% back, depending on how old you are, what your employment status is, whether you're a student, all these sorts of things. So next Monday, we're doing the sort of Jumpstart course. And then in a couple of weeks, we're doing the Advanced Computer Vision with Deep Learning course as well. So if people are interested, like I said, I'll upload the slides and then people can get them there. With that, I'm going to finish up and bring in Martin.
Hello.
Hello.
So let me just turn on some light. There we go. So we've got one bid for distance is Tokyo.
Yes.
In the region. Cool. Another one in Berlin, which is getting to like maximal. I mean, pretty amazing. I guess we want a New York person. Well, that will be 12 hours different, right? So
it is 6:30 in the morning in New York.
That's true. Okay. We've got to think of let's be realistic. Okay.
And it's 3:30 on the West Coast. Yes. All right, Matt, you ready to take over?
I will take over. There we go. Is this me? And also shout out if you see a problem. Okay, so welcome to my little section of TensorFlow Everywhere. What I'm going to do is just run through kind of a few little topics. So my name is Martin Andrews. I'm at raddragon.ai as well. And this is, if you haven't heard me talk before, I did a whole bunch of kind of finance and startup stuff. But after the financial crisis, I came to Singapore in 2013. 2014, I just had a kind of a sabbatical year, getting back into the swing of like research fields to figure out what is being done and what's interesting. But at that time, deep learning was on the rise, and buying a GPU got you somewhere. Since 2015, I've been kind of much more serious mode, much more Singaporean serious mode, doing natural language processing and deep learning. Both Sam and I run the TensorFlow and deep learning meetup here, and that has in part led to us being Google developer experts. We've also been doing research. Sam mentioned papers we've done, and clearly I've also got the Red Dragon AI t-shirt on for that. Okay, so I've got a few things to talk about. One of which is this tf.experimental.numpy. Then there's a TensorFlow profiler. And then there's some research topics done with TensorFlow. So there's a privacy topic and an NeRF in the wild topic. Sam has already mentioned kind of the next things we're going to do, which are events in Singapore. So courses. At the end of my thing, I'll talk a bit about courses. And I should say that in terms of our meetups, typically we'll go for something for beginners, something which is intermediate, and something which is kind of bleeding edge. Sam's talk I'd put as being an intermediate, because if you're a beginner, you don't really know why you would need all of this stuff. And so what we'll do is we'll do some extra stuff, either a beginner-friendly code and idea walkthroughs with the meetup, but also we do run these courses in participation with SG Innovate, or in partnership with SG Innovate, one of which is on Monday and Tuesday next week, which is Jumpstart. And Jumpstart is getting you from zero, hopefully you'll have done a little programming before of some kind, to actually building a project with, CNNs or RNNs or tabular data or whatever. So we have other courses too. I'll talk about that later. So we're also, apart from kind of this regular TensorFlow content, we'll also be doing deep learning, the cool stuff, because we know that a decent proportion of our audience loves the cool stuff. We love the cool stuff. Hopefully we can get people excited about deep learning. Okay, so I'm going to talk quickly about tf.experimental.numpy. And the point of this is to accelerate NumPy using TensorFlow. And so this is kind of a new thing, which is why it's in the experimental category. But the basic idea is you want to be able to run NumPy on your CPU, which you can already, but also on GPU or TPU. Now, this is something which couldn't really be done before, but now TensorFlow has brought in a whole bunch of these NumPy operations so that you can not only run these forwards, as you would do with normal NumPy, but you can also differentiate backwards through NumPy code. So you can write neural networks in NumPy as well, for instance. You can also use this same NumPy code with the TensorFlow APIs. So it could be the linear algebra stuff or the signal stuff or Keras. And so you can kind of mix and match the layers to do processing in the way which is most familiar. So this is one thing where Sam talked with the pre-processing layers before. Maybe you need to fix some stuff up with NumPy. Now actually you could do the NumPy things in TF NumPy. So the other thing you can do after that, and I'll show you just this quickly, is you can also compile this stuff so that not only can you run it like in kind of eager mode, one line at a time, you can also compile it down to run as a dispatch, like a pre-known dispatch, or you can actually get it to vectorize the code so it will run like super quickly. And so I've got a couple of examples. So here is just the very basics. Hopefully you can see this, or maybe Sam will embiggen this. I've got basically your pull-in TensorFlow experimental NumPy. They've chosen TNP. I guess you could pull it in as NP if you were really committed. And if I would just cover up this T here, this is just the standard NumPy kind of thing. This T, so there's random, rand, then clipping. So here's a bunch of random numbers, all clipped between plus and minus 2. We can now just check what device is it on, and we can see that yes, it's going to live on the GPU. So this is TensorFlow's made a decision. Okay, this can run on your GPU. The other thing is, because these TNP arrays abide by the same underscore array interface as NumPy does, you can use standard anything which is NumPy array can be run on this matplotlib, for instance, or other things. So hopefully they can get more interoperability with, say, scikit-learn to get things really quite nicely done. But this is kind of a work in progress, but certainly this is a nice thing. And if you're using other frameworks, you might be very used to doing .detach, .cpu, .numpy before everything. This doesn't need it. It's already NumPy aware sufficiently. So here's a quick kind of example of what happens with the performance. On the blue line, you've got standard NumPy, and this is what happens when you start to either put it on the CPU. You've got actually quite a big lift in terms of CPU performance, but partly because what it's doing is it's enabling this to be distributed across cores, across all of the different functions they've implemented, rather than just the kind of the BLAST library. But equally, they've got, as you move up, that this is actually in millions of array elements, and you can see that the GPU hardly blinks when as you increase the size, and so this is there's a clear win here. On the left-hand side, though, I should point out that it is actually slightly slower than NumPy for very small objects, because there's kind of a dispatch cost for launching these kernels. But any decent sized data, that's not going to worry you. So let's have a little just one more example. Here I'm going to take some data set from a tensor slices, but I'm going to generate a whole bunch of random numbers. So this is my little data set. I can now define a function which takes a gradient. So this is kind of a gradient tape thing, would be familiar to people who've done, say, PyTorch. I'm going to watch these weights. So this is my input and here's my weights. I'm going to do a dot product. So this is a NumPy dot product. And I'm actually going to take an exp from NumPy as well to actually do this is really a sigmoid, isn't it? Right. So I can then take a gradient across a NumPy object as well, or a quasi NumPy object. So this is kind of like you'd hope. And then you could initialize some weights and then run across the data set. Everything looks good. But also, because it's kind of interoperable, we can now say, well, let's use tf.math.sigmoid, because this is actually the math.sigmoid is actually kind of better numerically behaved than doing the raw operations in NumPy, because of these exponentials can get a bit unruly with big numbers or small numbers. So another thing you can do is you could also do a map function. So you can map this stuff across the NumPy arrays. All of this stuff is looking pretty kind of integrated within the TensorFlow system. But another thing you can do is you can actually say, okay, I want this function to now be compiled, and I also want it to be vectorized. So this thing will give me a compilation. And then this thing, when I vectorize it, now my GPU, basically this is creating kernels, I believe, of the whole operation and doing like extra compilation to make that cool. And so this shows the power of this thing once it's in there. So in terms of future directions, I mean, they've gone a certain direction, they've got a certain distance, but the in-place mutation of these NumPy arrays hasn't been done yet. So one thing you can't do is, here I've got, this is rows and columns, I'm just going to adjust the last column and multiply it by 2. That they don't do this yet. They're thinking about how they should get that done. So, but really, if you've got a matrix, that you can't just access elements and change them mutably yet. There's also going to be support for more ops. I don't have an ops list yet, but I guess at tf_numpy here you could. There's also the chances, what they're looking to do is getting this is a TensorFlow real-time kind of kernel thing, to get the operations dispatching quicker. They're also interested in getting the distribution across, say, multiple GPUs, like in hand. And they're also trying to go for scikit-learn compatibility, which would be awesome, because then you could GPUize all of scikit-learn, or big patches of scikit-learn, and also integrate with a thing called tracks. Now, this is kind of where me with my kind of detective hat on says, well, what's going on with tracks? Tracks is a thing which is built by the TensorFlow team, well, within Google. But the thing about tracks is it's actually built for JAX as well. So JAX is a thing which is using the back end of TensorFlow or the XLA compilation, and they're building yet another framework on top of these back ends. So this is kind of an interesting kind of aside, that JAX was built to use the XLA backend, and to do that, they've made it so that basically this is where the NumPy compatibility came from. Is this team was really wanting to write NumPy code, and then on top of that put a framework. But the same NumPy compatibility will also feed through back into TensorFlow, so you can use this in your TensorFlow code. So I don't want to like scare anyone that everything's going to change, but just also emphasize that when you hear about these new things coming along, they will actually have a positive effect on the whole of the ecosystem. Okay, so now let's move on to the next topic. So TensorFlow Profiler was announced about this time last year, and things have just got a bit more, bit more sophisticated. So TensorFlow Profiler, I'm going to do a little bit of a demo, so you can see what this is about. And let me go for this one. And what we have in TensorFlow Profiler, and this is a quick like MNIST example. What we're going to do, and this is a kind of a GPU thing, so we're running on a GPU here. We have a data set loader, and we're going to use MNIST. So this is not going to be a super difficult data set. And then we're going to have a data set pipeline, which is going to normalize it and batch it up, do kind of standard stuff for MNIST. Okay. We're then going to pass it through a simple model for MNIST. This is all standard stuff. And then what we're going to do is we're going to have this callbacks with the through TensorBoard, which has this profile information in it. So we'll do a little bit of training. And so now we're going to have a look and see what there's the standard TensorBoard stuff. Let's go to the profile information. Is a whole bunch of different information about what happened when. And what you'll see if you examine this, and this is my kind of takeaway, is up here in these tracks, there's a bunch of ops taking place here. These are each epoch, or there's stuff happening, but then there's a very large blank space where no good ops are taking place. And the ops are all taking place in this part. And what's actually happening, in fact, this TF data iterator get next, this TF data thing is making the GPU wait while it does its thing. So this is kind of identifying that the GPU is not being very well occupied, is waiting for the dataset loader to do its job. So then what you could do, say, okay, well, let's do the same thing again, but I'm going to add in a caching term and a prefetch term. So this is now going to try and cache the data set and suck it in all at once. And then we're going to run the same model again and see what happens. So now what you see is the actual compute is taking place like much more continuously, and there's the actual fetching, or the data set piece is taking much less of the time. So this is kind of proving that you can use these profilers to understand where are the bottlenecks in this pipeline, or where might I want to do an app function or something. Okay, so that's a quick intro. Now, just the new things which have been added are the Python tracer. So this is something where you have to switch it on because it kind of looks hard into your Python kernel as it's operating. You can now actually look at where all of the where all the time was spent in all of the functions within Python, and get this also out to this kind of nice profiling tool. So this is super handy. Even you just want to debug some Python code, this may be handy. But this is all integrated and will show up so you can have a look at it. Another thing which you can do is have a memory profile. So you can see, where is the memory being used? Am I getting, tons of objects being created, or is there just something sitting there which I'm, wasn't expecting to be there? So this is another nice aspect. You can also trace many more data points. Basically, this has been expanded in lots of different ways. If you've had a look at the profiler or were wondering about profiling, this is definitely a tool which has got more sophisticated, during COVID. So there's positive outcome. Okay, so now I'm going to talk about some cutting edge research in TensorFlow, and I've got kind of two topics here. The first is Sam?
I was just going to quickly suggest, because there's a delay, if people have questions for Martin, perhaps start asking them now, so that when we get to the end, they're there, because it does seem like there's a 30-second delay.
Right. I think there's some delay between the stream thing picking up the questions from the platform. So okay. All right. Let me start again. Sorry. Okay. So I'm going to talk about cutting edge research from the TensorFlow team. It's going to be in two pieces. First is about privacy, which clearly, being Google, we want to make sure that they are thinking about privacy. And the second is about this NeRF W kind of interesting, kind of cool pictures. So that hopefully that's a even more interesting. So TensorFlow privacy. Let's just kind of understand what could be done. Okay, so what we would like to do, or what Google, or what you as a company at your company might want to do, is learn all about your users by taking all of their data. Okay, and then once you've got this big database, you're then going to train your model. However, your users might not want you taking their data, or they might not want to give up their data. So suppose a single user represents this little piece of the overall picture. What does it seem like to them? Well, what we have is that little piece of in this case, it's the finger of the Mona Lisa. Here is the user's data that they're going to contribute, but they may be very wary about telling you exactly their data. So, if you've got a standard, privacy policy, you might say, give me all your data. But the world is changing. Now it's going to be saying, we will only use this data in such and such a privacy preserving way. And these are the kind of tools which will be needed. So here's the user's actual data. But what you can do is now say, well, let's flip 25% of the bits. So here, some of my data is being uploaded, but the person who's receiving my data doesn't know which has been flipped, and so can't make that much kind of accurate predictions about me. But when you assemble these all together, you can still learn the big picture across all of your users. So even though this is the a messed up version of the Mona Lisa, everyone can see that this is a Mona Lisa. And so this is why this preserves privacy. The actual individual user's data can't be used particularly specifically, but still you can learn a model over all your users. So they got a nice paper about this. There's a TensorFlow privacy blog. Sam has actually put together a notebook which has links to all of these things. So have a look out for that. We'll be adding that, I think, to the channel. So another thing which they have done, so that's kind of the basics of how this privacy thing might work. Another thing that you might want to do is measure how private is the data. Okay, so what they do here is they will take some private data, or the training data. They'll train up a model, and then they'll say, can I tell whether this input example was used to train the model? So if I can build a classifier which is really good at detecting whether an input was used to train a model, then it means that training piece of data is pretty much inside the model and could be extracted out by someone probing it. On the other hand, if my kind of probing system cannot determine whether the input data was in the training set, then it means your training examples have been effectively hidden by this process. So that's kind of what you want. You want not to be able to tell, are these examples in the training data, or are these specific examples in training data, but more like, am I part of the universe of the training data that we yes, you seem to be part of the universe of training data, but we can't tell who you are. And so training this, basically this is kind of an adversarial thing, and you want the model to be as good as possible, but you want it not to be able to tell, was the example in the training data. So the comment in the Google Notes about this is, look how simple the API is. And so, okay, I will take their word for it that this is a simple API, but they're clearly putting work into making it so that it's possible to do this privacy-aware training with two goals, one of which is to make your model great, and also to make it so that this kind of these attacks of discovering what data was added won't work. And so basically this area under the curve, if you can actually detect whether something is in the data set, actually privacy's gone down. So basically you want to make the area under the curve for these attacks to be as little as possible, so you've got as much privacy as possible. So this is kind of a nice suite of tools where Google, showing that they actually do care about these things. But at the moment, it's pretty much, while there are tools to use, this is also something which academics are very interested in. So clearly they're working with Princeton or something. Anyway, so here's a link to their stuff on privacy. It's interesting read and kind of lets you know where they're thinking of going with their tools. Okay, so as a last piece on the research, let's talk a little bit about NeRF in the wild. So NeRF in the wild is neural radiance fields for unconstrained photo collections. And so this in the wild is kind of a something which is added on because NeRF itself is a previous paper, okay, from another group. So the idea here is they want to be able to take internet photos which have been taken, basically people will take these from any angles, any time of the day, weird cameras, and maybe with like people in the front or odd things going on, and they want to construct a perfect model of the, a very visually appealing model of the underlying thing. And the question is, can you do this? And hopefully, Sam, is the frame rate okay?
It looks good, yes.
Okay, awesome. Okay. So, they've got some little animations. Okay, so the method here, this is a Google slide deck, and they've kind of come up with this as being the explanation. I don't particularly like this explanation. And Sam, am I able to wave my hands around?
You can wave. People can see you, yes.
So what we're trying to do is build a 3D model from photos, okay? And this, in some ways, you might think, well, this is very difficult to do because, am I going to use Blender or Unity? I'll build a careful model, and then I can look at it from different angles and see what the photo should be. But the problem with that is it's not very neural. It's not easy to learn how to construct this model based upon gradients. And so all of these methods want to use kind of gradient information, because then you can learn these using GPUs, and previous methods don't work nearly as well. So, okay. So the idea here is, rather than build an actual model and see what it looks like, I'm going to build a neural network which would say, so instead of having this model within this, this volume here with here's my statue or my gateway, instead of having a model here, basically I'll have a neural network which says, if a ray of light is coming in from this angle, what would it hit? And rather than actually having it hit actual kind of 3D models inside, my neural network will just answer the question. Well, this segment of the ray hit stone, and this segment of the ray hit something, and this was air at the back. But basically, the neural network is not going to tell you like what the actual model parameters are, or what the 3D model structure is. They're just going to be able to answer questions about what is there if I were to have an array. So basically, these little neural networks, which here we go. These little neural networks are saying, if I were to go through the picture at this position within my actual photograph, and I scan through the model with these little line segments, what color would it be? And so I run it. In this case, it's got 5 different samples. I run the thing 5 different times. And here, what I'm going to do is I say, I'm entering at this XYZ angle, or the XYZ position, and at this angle through your model. Now tell me what you see. And so this model will come back saying, I see this color, and it's this dense, i.e., how transparent is this? Or how opaque is this? So the actual 3D model doesn't really exist in terms of XY coordinates. The 3D model is just suggested by whatever this neural network says about rays coming through the, you give it some X, Y, Z, theta, and phi kind of coordinates, and it just says, okay, here's the color, here's the density. Now these models, you'd think this was a crazy scheme, but the alternative might be to have a model of a volume which is 1,000 by 1,000 by 1,000 voxels, and I then record the color of every single one of those. But now I'm dealing with a gigabyte or a giga color in order to look through this volume. By doing it with these neural networks, instead of having a discrete element for my volume, I'm just going to ask the question, if I fire my neural network, if I fire my ray through, what would I hit? And the neural network will give me an answer without ever having to look anything up. So this is kind of a very strange arrangement to actually model this thing. So the end result of this is that these models, this is the same model again and again and again, but these will have like 5 million parameters or something. So instead of a billion discrete colors and opacities, it will be 5 million parameters, which would explain how every ray would interact with the model. So this is kind of what they're doing. They're projecting through all of the photos. First, they work out where the photos are by some other method, like relative to each other. And then they just say, well, I want, if I shoot my rays through every element of this photo, I want the colors suggested by this whole process to match the color which is on my photo. Okay, yes. And so they have a code sample here which kind of explains it, but basically they just say, okay, we're going to walk through each of the points along this ray, and then total up what the predicted color is and what the cumulative opacity is, or transparency. So this is kind of, I'm not sure this is a particularly helpful piece of code. The bigger picture is kind of more what's helpful is that this neural network's going to answer about colors rather than having an actual model of what the color is, in kind of terms of 3D planes or pictures. Okay, so here we go. This is, now I'm going to explain just one more thing, is that the actual pictures, even if you've got a great picture of this, I don't know, this gate, it may have been taken at sunset, or it may have been taken during the day. So there could be a whole bunch of other like color stuff happening, which would make all of the photos different in different ways. And so what they do is, along with each photo, they also have an embedding, which basically they leave floating. And so this embedding, they also are training this to make the photos, in order for the photos to agree with each other, all of their embeddings will change. And so it will learn about how this model behaves against the different embeddings, and conversely, what these embeddings mean for each different photo, or what embeddings are associated with each different photo. So this is to try and remove the lighting effect for all these different photos, because they want to do it with tourists' photos. Okay. Another thing is that there are lots of people in these. In this photo here, there's a bunch of people on this side, and there's some other different people here. They moved, or it could be there's a hamburger stand or something, right? Which that isn't always there, and so they also have an embedding which suggests which part of the image should I kind of blank out and ignore in order to produce the actual model. And so clearly they want to, since you're going to ignore it, you want to make that space as small as possible. On the other hand, you do want to remove it, because otherwise you get all of these artifacts drifting around your finally generated model. And so this is something where this in the wild thing is now being applied, whereas before you had to take beautiful pictures all under the same lighting conditions without anything in the way. Now they can do this with regular people's cameras from anywhere, any time of day, even if there's stuff in the way. So this transient embedding is also learnt, that they learn from each photo what parts would have to be ignored to make it consistent. So, okay. So having done this, okay, here you see in this photo down here, they've got people in the way, but if you mask them out, they wouldn't be there. Makes sense. So here's kind of the results you might get from different, these are different famous sites. There's on the right, we've got a fountain. In the middle, good question, maybe Sacré-Cœur. And there's Brandenburg Gate on the left. And this is, you can see that in particular on the Brandenburg Gate, there's some kind of artifacts around ground level where it hasn't quite been able to get rid of stuff perfectly. Maybe because there's stuff like, there's normally problems there. There's normally people loitering there. On the other hand, when you're looking at the actual detail in these things, it's quite incredible what they're able to back out of photos taken in the wild. Okay, so not only that, but now they know how the model reacts to different lighting conditions, they can also say, well, what happens if we impose that embedding on our camera or on our synthetic camera? So they can then say, well, let's look at this scene using different cameras, which they can now move around the scene, as a movie. This is kind of, these embedding things are like, there's a super powerful technique underneath all of these things. And this is kind of where we're going. Okay, so there's some links here, and this is the team who's working on it at Google. We've also got some of these links are in the notes handout we have. So this will give you, ample place to go and have a look. I guess there's one thing which I should point out is there's actually code written in TensorFlow for the previous generation of this NeRF. If I just skip out of here and this NeRF in the wild, no. Okay. The NeRF in the wild website is cool because there's actually more videos about what they're doing. Lots of nice stuff there. But the NeRF code is actually produced by this other team, I guess somewhere at Google Research. But it describes how this radiance field thing works, but also it has some sample data sets, so you can then go and actually train your own model. It takes about 15 hours on a GPU kind of thing. So this is something which you could have a play with in a weekend. It's my guess is for the other ones where they're backing out very high resolution images with all of the embedding stuff. That's going to take a bit, quite a few GPUs to do. But it's nice that there's code which, accessible at least. Okay, so
Martin, how about you take a question now?
Sure. Okay.
You've got a question about the privacy stuff. So can you read that?
Oh, sorry. Okay, you put it on the main screen. Could we infer the? So I guess the answer to can we infer the exact example is Probably not. I guess if you could pick out the exact example, it's very, very revealing, and so you're optimizing your model against being able to do that, right? So this is where you would then up the noise so you can't possibly overfit the model, right? If that makes sense. So the fact that if you can actually overfit this thing means that the noise wasn't turned up high enough to preserve all the privacy you wanted. So this allows you to kind of gauge how private your model was, and can you make it more private by finding these examples. On the other hand, there's another nice paper called Tracin, which Google released maybe 2 weeks ago, where what they're doing is they're trying to do a kind of analysis of how much impact does each training example have on your model. So this is kind of interesting. This is not a privacy-directed paper, though there's clear parallels. What they're interested in is, can we detect bad training examples? Because if I train a very general model across a whole bunch of data, and there's one training example which is really difficult to learn, it could mean that that's a mislabeled training example because it's way outside the distribution. So there's a bunch of other interesting things going on with, like, detecting, it's kind of an explainability. All of these things are now kind of connected: adversarial stuff, explainability, and privacy. It's kind of a nice synergy between these things. So yes, I'm not sure. Hopefully that kind of answers your question by kind of mushing around as an answer. Okay.
Do you want to do the wrap up and move on to Robert?
Oh, okay. So someone's mentioned it. So is this? Okay, same person asked, is this like compressing information into? So I guess you could think of both of these research topics as compressing information. Clearly, if I'm wiping away exact examples from the overall model, then the generalization has kind of wiped away some of the specifics. So that's interesting. Equally, you can think of the NeRF example, which is the radiance field thing, as you're really compressing the gigabyte of voxel information down into 5 meg of ray tracing. So there's a whole interesting representation question here. Anyway, this moves on to yet more papers to talk about. So anyway. All right, Sam. So what's next?
Do you want to wrap up and we move on to Robert's talk?
Okay, sure. And then I can talk a little bit more about in particular, the beginner-friendly jumpstart. So anyway.
Okay, so how about we do Robert first and then come back to you, yeah?
Sure, absolutely, yes.
All right, so let me...
Hi, I'm Robert Crow, and today I'm going to be talking about...
Let's just...
Okay.
Okay, let's let Robert take over.
Hi, I'm Robert Crow,
yes.
And today I'm going to be talking about ML engineering for production ML deployments, and specifically about TFX, the open source platform for production ML. Let's get started. First, let's discuss production ML and change. There are easy problems where the ground truth and the data change slowly, like months or years, or never maybe. So for example, recognizing cats and dogs don't change very quickly. So model retraining is typically driven by model improvements or better data or changes in the software or systems. Labeling is fairly easy for these kinds of problems. It gets a little more difficult when you're dealing in domains where the ground truth and the data does change, maybe on the order of weeks. And in this case, model retraining needs to be driven when model performance declines, as well as with model improvements and so forth. And labeling becomes more of a challenge in these domains You can either use direct feedback from your systems if that's an option, or maybe crowd-based. There's a number of ways to apply labels. But it gets really hard when you have ground truth and data changing on the order of days or hours or even minutes. So situations like trying to predict markets or many real-time scenarios, this is a very difficult problem. And model retraining and declining model performance go hand in hand in these domains, and labeling really becomes a challenge. So it's these kinds of production ML scenarios which were the reason that Google developed TFX. Fundamentally, Google needed TFX because we have a ton of applications that use ML in production and mission-critical applications. And you can see this across Google and actually across Alphabet. And you can see it in many of our partners as well. Twitter is an interesting case here because they actually came from a torch-based environment where they had a significant investment and moved to TensorFlow largely because of the availability of things like TFX. Here's a sort of a high-level look at what TFX is. On the top, you see tasks that are performed as part of the process of training a model. So you're ingesting data, and finally you have a trained model and you're going to serve it. In the middle are libraries, and those libraries are also available as open source projects, and they can be used by themselves. But the components of a TFX pipeline leverage those libraries and create a pipeline for ML training and also for ML inference as well. This is sort of the canonical TFX pipeline. You could think of it as a hello world pipeline. In it, the orange components here are the standard components that come out of the box with TFX. But I want to emphasize that you are not limited to these. These are just where you start from. So we'll talk about each of these components. And on the right, we have the deployment targets that are available from TFX. So you might be deploying into a serving cluster in TensorFlow Serving, or a mobile application with TensorFlow Lite, or a JavaScript application, or into something like TensorFlow Hub if you're going to reuse that model maybe for transfer learning and later. So what is a TFX component? A TFX component is essentially a task that you perform in your ML pipeline. It has a configuration, and it gets its input from metadata. It's taking input artifacts from metadata, except for the very first component that's ingesting the original data set from some data source. It takes those inputs using an input channel, it does its task, and then it takes the result and creates a new artifact and puts that back into metadata through an output channel. And that's how components communicate with each other. An upstream component will produce an artifact that downstream components depend on, and data flows through the pipeline by flowing through these dependencies in metadata. So I've mentioned metadata. Let's talk more about the metadata store. Metadata in the metadata store powers some really significant functionality. First of all, it allows you to trace the lineage of artifacts that are produced. So for example, if you want to find out what data a model was trained with, it could have been trained months ago, you can trace that back by using metadata. You can also use metadata to compare previous training runs. So again, I may be retraining a model that could have been trained last months ago, and I want to compare those training runs to see why has it changed over those months. It also allows me to reuse previously computed outputs. A component and the tasks in machine learning can take quite a bit of resources and quite a bit of time to run, especially with large data sets and large models. So if the input to a component hasn't changed, I don't want to rerun that component. I just want to pull the last result from cache and reuse it. A lot of what TFX does is accomplished by distributing processing over a distributed cluster using Apache Beam. Apache Beam supports a number of different types of distributed clusters, including Apache Spark, Apache Flink, and Google Cloud Dataflow. And it supports a number of different languages through SDKs. So putting Beam in the middle, we have an SDK where we're going to make a call to Beam to define a Beam pipeline. That's going to get translated to the native API for whichever cluster we're running on, and a result is produced. Let's look at the TFX standard components. So again, this is the Hello World pipeline, and these are the standard components. But again, I want to emphasize you can create your own custom components, and there's 3 different ways of doing that. But let's talk about these standard components just so that they're clear. First off, we have to ingest our data, so we're going to use ExampleGen for that. ExampleGen is going to take our data, ingest it, split it, and save it off as TF examples in a TF record file. Next, StatisticsGen will make a full pass over that data and calculate statistics about it. That's important when we're in the part of the ML development process where we're trying to understand our data, or if we have a new data set and we want to see what's changed. SchemaGen then calculates a schema across our data. What are the types of each of our features, and for categorical variables, what are the valid categories? Example Validator takes both of those results and looks for problems. Things like examples that have the wrong type in a particular feature or a categorical value that shouldn't be there. Transform is where the feature engineering is done. And Transform will convert the feature engineering that we want to do into an input graph that becomes part of our model. Trainer takes that graph and the model that we've defined using TensorFlow and trains our model. Evaluator takes that trained model and does a deep analysis of the performance of that model. By deep analysis, I mean it's not just looking at the entire data set, it's looking at individual slices of the data to try to understand how performance varies across different parts of our data set. Infravalidator makes sure that we can actually deploy our model to our serving infrastructure. And if both evaluator and infravalidator agree that yes, we can deploy our model, and evaluator has checked to make sure that the model is actually better than what we already have in production, then Pusher will push it to one of our deployment targets. And we talked about these: TensorFlow Serving, TensorFlow Lite, TensorFlow JS, or TensorFlow Hub. TFX also supports mobile and IoT deployments through TF Lite. So TF Lite support in TFX is used to train, evaluate, validate, and deploy TF Lite models from TFX pipelines. And there's really only 2 changes that you need to make. You need to invoke the TF Lite rewriter that happens from within Trainer, and then you need to evaluate that model using the TF Lite model for evaluation. I've mentioned a couple of times that TFX allows you to create custom components. Let's take a deeper look at that. First off, you can create a component by customizing the executor of an existing component. When you do create a custom component, it fits into your pipeline just like any other TFX component. And there's 3 ways to create a custom component: using a Python function with a decorator and annotations for the arguments, or using a container where you can be implementing whatever task you're doing in whatever language you need, or extending existing component classes. TFX is also supported on Google Cloud using the Google Cloud AI Platform pipelines. Let's look at that. At a very high level, this is what the architecture looks like. TensorFlow is running on TFX, which in turn is running inside Kubeflow pipelines. And that's running on the Google Kubernetes engine, or GKE, and leveraging the Google services, the cloud services, managed services, that are available on Google Cloud. At the end of the day, it's the same pipeline. Now let's take a look at 3 different ways to run a TFX pipeline when you're doing development. In the demo today, I want to show you 3 ways of developing with TFX. And to start with, we'll just create a complete TFX pipeline in a notebook, in a Colab notebook. And we won't actually get through the entire pipeline, but we'll get through the first few components, and the rest are very similar. So let's get started. I'm going to just jump over the explanation. This notebook, by the way, is available on the tutorials page of the TFX website. I've already run this once, so these things are preloaded so that we can save some time. Okay. Normally on the first run for this, you need to restart the runtime because of the way that Colab loads packages. So now we're going to import our packages. Okay. Let's check the versions, make sure they're good. Now, this is actually version 22. We just released version 23 this week. Set up the paths, and this is the Chicago taxi example. Okay, we've got path to our data. That's what the data looks like. This is a CSV file. And now we're going to create the interactive context. So the interactive context is a key part of running in a notebook. Essentially what this does is it allows you to orchestrate a pipeline by stepping through notebook cells, and the interactive context maintains the context while you're doing that. So very useful for this kind of development. All right, and now we're going to run our first component, which is example gen. That's where we're going to ingest our data and split it. Okay, now at the end of each component, after you run each component, you'll see one of these. It's the Artifact Explorer, and it lets you explore the artifacts that were imported into the component and the resulting output from the component. So this is example gen, and I can look at the inputs that came through this input channel. And in this case, it's a external artifact. It's that CSV file, and the outputs. So the outputs are our split data set, and there's our split. We have train and eval by default. Okay, let's keep going. So now we're going to just take a look at the artifacts in a different way. That's just more of a Pythonic way to look at it. And we can look at individual examples that were ingested, and they look good. And so we're going to run our second component, which is statistics gen. Statistics gen is going to calculate statistics across our data set. We get, again, an artifact explorer for statistics gen, but let's keep going because there's a really nice UI for statistics gen that comes out of TensorFlow Data Validation, TFDV, and it allows us to really explore the statistics around our data set and our different features, including looking for the number of missing values and things like the valid categorical features. So really useful to be able to explore your data set. We're in the part of the ML development process here where we're really trying to set up our data and understand our data set. So let's move to the next one, which is schema gen. Schema gen tries to infer a schema from your data set. What are the types of your features? Now, you do need to think about making sure that it got it correct because it'll make a best effort at doing that. But you may know more than schema gen does. So if things need to be adjusted, you can do that in the artifact that's produced by SchemaGen. Okay, we're going to stop there and move to the next style of development. Okay, the next environment we're going to look at is running locally on a desktop or a virtual desktop. We're going to be using Jupyter Lab with a notebook, and we're going to be using an IDE. So to start with, I've copied the Beam template into a folder on my system and started up Jupyter Notebook, which is open here. And let's go ahead and run through the notebook, at least the beginnings of it. One thing to be careful about, since I'm not running in Colab, I already have TFX installed in my virtual environment, so I'm not going to run this cell here. So we'll go ahead and set up some paths, check our version of TFX, which we've already installed previously, and set up some other variables and check our pipeline name and project directory. And then at this point, we're going to copy the rest of the template, the other template files, into our project directory. And we're using the TFX CLI to do that. So we'll go ahead and do that. And you'll see that I don't have CUDA loaded. So we see some errors around CUDA. That's fine. It's just telling me that I don't have CUDA. And then in the notebook context, we change into that directory. And then we can browse the files as sort of a sanity check and run some unit tests on our files too, which is always a good idea. Okay. So we copied our template into the project directory. Now we're going to create a pipeline for the Beam DAG runner to run. Now we're not running it yet, we're just creating it. Okay. So actually it's telling me it already exists because I ran this once before. So now we're going to run our pipeline. So again, using the TFX CLI here. See that right here. And we're using a run command. So at this point, the only component we have in our pipeline is the example gen, which is in this case reading from a CSV, and you can see it's finished. Okay, so now let's move on, and we'll add some components. So to do that, we can do it a couple of different ways, but I'm going to go into an IDE. I've got VS Code running here, and these are the files we're working with. This is actually the template that we're running in Jupyter Lab, so I could be running all of this in VS Code too. But where I want to add those templates, those components, is in my pipeline file. So I'm going to edit pipeline.py. And you'll see the way this is structured, it's really easy to create this first sort of hello world pipeline using the Chicago taxi example. Example gen is already part of the pipeline. Statistics gen is defined, but it hasn't been added to the pipeline. So all I have to do is, uncomment that to add statistics gen. And let's add a couple more. Let's add schema gen and example validator. And let's add transform because we want to do something here with transform. So I'm going to save that file. And in transform, there's some user code that we're going to be using. And this is where we do our feature engineering. So there is a function in in our preprocessing.py file called preprocessing function. That's given to the transform component, and transform runs that to do preprocessing or feature engineering on our data set. So what I'm going to do here is set a breakpoint there, and then I'm going to run the beam DAG runner here. So I'm going to go to the debugger, and I'm going to start up the beam DAG runner. No, I'm sorry, wait. I have to update the pipeline first. So this command right here, I'm going to run. And in fact, I'm going to comment out the run command so that I'm only doing the update. Otherwise, it would run it twice, and that's fine, but I don't want to do that. So we'll go ahead and run that. It'll update the pipeline for me, so it's going to add the components that I just added, which are statistics gen, schema gen, example validator, and transform. Okay. So now, if I run the beam DAG runner in the debugger, it's going to run my pipeline. And it's going to hit an error that I caused when I edited the file, which is okay. So that's all right. We'll stop that. We'll edit our file. And it was complaining about one of these here. Oh, I need to edit pipeline.py because that's where, yeah, I got an S from just bad typing. So let's save that, and we'll rerun beam DAG runner. And there we go. We hit our breakpoint. And we have variables here that we can inspect, including our features. So for doing IDE style development, you could actually do it in a notebook or the IDE or both. This is pretty handy. Okay, the next style of development that we're going to look at is on Google Cloud, where we're using Cloud AI Platform pipelines to run a TFX pipeline. And this is running actually on top of Kubeflow pipelines. So you have, in this case, a Jupyter Lab instance that you're going to use with a template that's very similar to the template we just looked at with the Beam Orchestrator. Not like the interactive context we looked at first, but the Beam Orchestrator, where we're setting up our components and then we run our pipeline. So very similar. We're using the CLI down here to first create our pipeline, and then when we make changes to our pipelines, we kick off an update and then a run using the CLI. So very similar process. And again, you have the same sorts of files. They're here in my project directory. So the pre-processing function is just like we looked at just now in Beam, although I can't set breakpoints in Jupyter Lab. And I add and subtract components here in pipeline.py, just like we did previously. So we have that environment, and we also have Kubeflow pipelines. So this is the notebook that we're using. That's the template that we just looked at. We can also look at our pipelines in a graphical view to see how things are put together. And we can also look at experiments in very much the same way. So there's an experiment that we run, and you'll see it's been marked as successful. We also have artifacts that we can look at, and there's a nice tool here that allows us to look at the lineage of artifacts and understand how they flow, how the data flows through our pipeline. So a lot of great tools here on Google Cloud. I encourage you all to look at it. I know this was really fast, but hopefully this was useful. Thanks very much. And that's TFX. It includes standard components for your production needs, and you can also create your own custom components. It's flexible at several layers, including orchestration and metadata. We also have a new blog post out that explains the history of TFX, TensorFlow Extended. I encourage you to take a look. And here's our website if you haven't seen it before. And here's some links to help you get started. And that was a really quick overview of TFX. There's lots more on the website. If you need to put an ML application into production, I strongly urge you to take a look at TFX. It's what Google uses. Thanks for watching.
Okay. All right. So for those of you who are still here, sorry about the code. I think was pretty small to see on the screen for that. It wasn't necessarily what I thought it was going to look a little bit bigger. But anyway, Martin, do you want to do a wrap up quickly?
Yes, I'll just go through some of the kind of the things. I guess in context, we should also say that if yours was kind of an intermediate thing, I did the NumPy was pretty intermediate, and the privacy was kind of intermediate level of explanation. But the research got kind of the NeRF thing is kind of an advanced and cool topic. So on the other hand, this was overall, we would say this is probably not a very beginner-friendly start to the year. And so I just want to kind of emphasize that we do talk to beginners, and we love beginners, in fact. So shall I talk a little bit about that? Yeah.
Go for it. Yep.
Okay. So let's just hope. Here we go. So Sam mentioned this before. We run a series of workshops. We have 5 currently in the kind of the roster of different modules that people can take. But the first one of this is called Jumpstart, and the next run of this is Monday and Tuesday next week. And so there are still spots available. But it's going to be online, but us talking live, so it's kind of ask questions at any time. There's 2 weekdays of content. People also get to watch videos and answer some questions, but they can also, as well as playing with these real models, so it's kind of hands-on. But we also have kind of pick a project. So if you're doing kind of a startup and want to add some AI, make that your project. There's lots of different projects that people can do, but one thing we like people to do is if you have some kind of passion about something, do your own project. This kind of takes people away from I did a project on Coursera, or I did a project as part of a team at university on their resume, to I did this because I care about it and I can talk about this project. Right? It's a very different mode when you're talking about having done something on a resume, to have actually done it for yourself and learned something which you can talk about. There are some certificates or whatever, but basically, once you pick a project, we do have some kind of backup projects if people can't think of anything. On the other hand, we're going to try and make your project a success, and we kind of also kind of gauge how difficult it can be. But we also want it so that it's difficult enough to make sure you've actually trained something and learned something. One thing we should point out is that this is done in conjunction with SG Innovate. Their website looks kind of like this. And if you go into the talent bit, you'll see a whole bunch of modules. If we go into this module here, this is the Jumpstart, which, as I said, is Monday, Tuesday. Basically, there's stuff about gender, pricing, trainers are me and Sam. But there's the funding support it's not just if you're old, but basically the kind of minimum funding you're going to get is like 70% off. But there's, there is very generous funding. Congratulations to the Singapore government to realize how important upskilling is. Basically, that's kind of that makes this work well. And it's, in some sense, the funding makes this kind of a no-brainer for learning something and getting kind of good resume points. So I guess the other thing I should point out is, if I go back, can I go back? Sorry. There's also another one coming up with advanced computer vision. So the basic jumpstart will get you training CNN models and using ImageNet and things like that. The more advanced computer vision will have object detection, so you can actually kind of localize things or count things or do facial recognition. All of that would be in the advanced computer vision. The advanced natural language processing will move on from the basic sequence kind of processing, which we do talk about in Jumpstart. So we could do, in Jumpstart, you would learn how to do basic classification of text, maybe generating some text. That's in Jumpstart. But once you get over to this side, on the advanced things, you'll be talking about transformers, all of the kind of the latest stuff. And beyond that, and so this is kind of moving into, beyond April, we have some kind of much more researchy module and a much more production module. So this is where to start. It's possible, if you want to do this if you want to do an advanced module without having done Jumpstart, we would kind of require a test, because what we find is that people who just jump into module 2, having done, I did all Coursera and everything, they're not quite as fluent with making a model and getting it training as you might imagine, just because Coursera will kind of hold your hand and it's kind of a fill in the blanks deep learning. Whereas we kind of want people to actually get their hands dirty and make a thing which works. Anyway, so that's kind of a bit of an advert for these paid courses. And we would love to see you on next week if you could make it. Anyway, the next event, I guess, is the show must go on. Now, we really have to do something in this post-COVID world. Clearly, most people have been to this TensorFlow and Deep Learning Singapore meetup site. There's a lot of us now, so it's 4,400 or something. It's going quite well. But of course, more would be welcome. And also people from further afield, I guess, is welcome, just because we're not constrained to being just Singapore anymore. We might as well talk to the world. We're going to be trying out some different formats, one of which will be different from what we've done really before, is to have kind of like a beginner friendly kind of code and idea walkthrough. So we'd be taking fairly simple models and then kind of explaining, like, why is this, not only what does this line of code do, but like, why do you want to do that? And so this kind of code and idea walkthrough we think is probably good for beginners. We probably won't start at the like with the big picture stuff that Jumpstart will and introduce everything in context. We'll be talking about fairly specific stuff. On the other hand, this is something that you could join and just see whether you like. That will be another avenue, because we know there are a lot of beginner people who are coming along who just want to dip their toes in the water. The next one is probably in about a month's time, more back into the kind of the normal TensorFlow and deep learning thing. But this next one will be definitely a deep learning focus rather than a TensorFlow. This one has been super TensorFlow intensive because this is a TensorFlow everywhere event, according to the Google global TensorFlow everywhere initiative or whatever. Our next one's going to be much more about deep learning. Sam and I we read papers, we engage in Twitter and Reddit or whatever. We love to stay on the ball. There's so much cool stuff happening. Even though a new AI winter's being declared like every couple of months, there's tons of new stuff happening. We don't exactly know what papers it will be. I know someone asked in the questions that, tell us the papers ahead of time. It may be we've got a good idea, a week ahead of time, but it may be that something really cool comes up 2 days ahead of time, and there's just not, we're struggling to see whether we can say something interesting about it. We would, we like this stuff. Yes, so if you're up for the kind of more advanced look at this, then absolutely. Or even if you're a beginner but interested in see what can be done, this is going to be in like a month's time. Okay. Thank you very much, and Sam as well. If you have suggestions, please let us know either in the comments here if you're watching on YouTube, or on the TensorFlow and Deep Learning Singapore. There's kind of a suggestions thing. If you would like to give a lightning talk, that would be very welcome. If you're worried about talking like off the top of your head, then Robert was, mainly because of time zones, but Robert was fine to pre-record his, so at least you could get out, you could try it a couple of times and give us the best one or something. We'd be happy with that. But we will welcome these lightning talks. Also, giving a lightning talk, excellent resume point. Talking in front of people is always good. Good motivation and good practice. All right, so Sam.
I think that's it. Is Jiaxin going to join back to finish up, or we'll just close it out? I'm not seeing her come back. She may have gone to sleep. We've gone for so long. So
okay, we can close. We can close. Okay.
We can close it. All right, everyone. Thanks for coming. I know we ran a bit over time, stuff like that. But yeah, we're definitely going to be redoing, doing more meetups going forward. Like Martin said, we're looking at doing some beginner stuff. If you've got anything particular that you would like us to see us do, let us know, or leave a message, either, I guess, on the video or on the meetup. That would be great.
Yeah. Right. And looking at the comments, if anyone would like to talk about chips, that would be great too, right? For instance. It's good to see people that we remember, and we would welcome getting the community together again. So,
some other people we know too. We can't see your names unless you write a comment. So hi Corey, hi Brahim. It's good to see you. All right, I guess we finish up, and we'll talk to everyone soon. Thanks.
Okay.
Good night, everyone.
Cheers then.
Bye.